All right, here we go. This is a little bit of Chapter 4, very beginning of it, which is a look at matrices. And we're actually looking at matrices for a couple reasons. One is that they're kind of cool and you can do some neat mathematical things with them. They have their own properties. But two, they will lead to a fourth and very calculator driven way of solving systems, which can be particularly helpful when the answers are irrational numbers. They're ugly numbers. So anyway, we have matrices, which is the plural, a matrix, which is singular. The definition of a matrix is a rectangular array of numbers enclosed in brackets. And brackets are what really make it obvious that you're dealing with a matrix. Here's an example. Really easy one. 1, 2, 3, 4. 4 members in that rectangular array enclosed in brackets. The dimensions are the number of horizontal, right? That's this way, horizontal rows by the number of vertical, that's this way, columns. Whoops, columns. Okay, so the size of this one would be that there are 2 rows, 1, 2, and 2 columns. So up above, it would be a 2 by 2. Let me give you another example. If you had a 1, 2, 1, 1, 4, 6, 8, 3, and let's add a -2, a 0, and a 99, just for fun, because we can. If you looked at the dimensions of this, you would say it has 3 rows and 4 columns, so it would be a 3 by 4. Everybody see that? 3 by 4. Okay, what's interesting is that we also, within these matrices, we have an entry. And the entry is a member or an element of the matrix. So, for example, if this was our matrix and we said M2, 3, member that's on the second row and the third column, and that would be equal to 5. So we had in our matrix 1, 4. See if you can figure out what that would be. First row, fourth column, -2. Okay? So we've got the definition, a rectangular array of numbers enclosed in brackets. The dimensions are simply the number of rows by the number of columns. And the entry can be found with this entry address, which tells you where in the matrix to look. Okay. All right, let me just erase that. My fancy eraser. I hope some of you have had matrices before. You might ask, well, when would you ever see these in the real world? Let's see, before we go on, maybe I'll, sorry, get more Kleenex. Maybe I'll give you an example. Let's say that you did some inventory, and my sister and brother-in-law have a sporting goods store, and we're constantly counting, how many large t-shirts there are versus medium, small, and so forth. So if you had a way of arranging them, such as small, medium, large, extra large, and let's say you had 3 different colors, red, black, and yellow. So you had these different types of shirts, different sizes, and when you count them, this is what you found, 15 mediums, 8, 2, 0, 0, 7, 12, 0, 0. So that's how many you found of each of those in the different sizes. Well, let's say you want to double your inventory. It's possible to represent that as a matrix, and then multiply it by things, add things to it, find the value by multiplying by a price matrix, and that's some of the things that we'll look at. But this is just how this whole matrix idea might get applied to the real world. Okay, so matrices have some properties. If you had something like 1, 2, 3, 4, and you wanted to add another matrix, 2, 2, 3, 3, the way this is done is simply by checking first to make sure that they're the same size, and this is a 2 by 2, and this is a 2 by 2. So because they are the same size, we can multiply, or excuse me, add the corresponding entries. So our sum would be 1 plus 2, which is 3. 2 plus 2 is 4. 3 plus 3 is 6, and 4 plus 3 is 7. So this is the sum of these two matrices, which we are able to do because they are the same size. Otherwise, the corresponding entries would not match up. Okay? So this would work for both addition and subtraction. Addition and subtraction. All right. The other thing to consider, the other operation, is what's called a scalar multiple. And I alluded to this when I talked about the inventory. If we had a matrix 1, 5, 8, 2, and we simply wanted to increase this by a factor of 3, we could multiply the whole matrix by that, which means that every single entry is going to be multiplied. It's almost the distributive property of matrices. So this will give us 3, 15, 24, and 6. And that would be the product of 3 times that matrix, 1, 5, 8, 2. By the way, when you read a matrix, so if I were to read this one, I would read the first row, 3, 15, pause, 24, 6. So I would read it once again, 3, 15, 24, 6. And we'll all get used to doing that in class. Okay, I think that covers that first part. What else do we have? Oh, I know. Excellent. Properties. Those are some of the operations. Properties are interesting. Properties are the ones that you know from real numbers. Ooh, not that. Silly. First one is commutative, which means does A plus B equal B plus A? Picture that. Picture an example. 1, 2, 3, 4 plus 4, 0, 0, 5. Would that be the same as 4, 0, 0, 5 plus 1, 2, 3, 4? What do you think? I think definitely commutative property will work. How about associative? Associative, if you remember, is the regrouping property, which says that A plus B plus C is equal to A plus B plus C. Does that make sense? I'm going to give you an example. 1, 2, 3, 4. A equals that. B equals 4, 0, 0, 5. And C equals 1, 0, 0, 0. And I want you to do this out and tell me whether or not the associative property holds. I'll ask you in class. Okay, the third one is the additive identity. And the additive identity in the real number system, if you had 2, what would you add to that to get 2? Obviously 0. Well, the matrix equivalent to that is if I had 1, 2, 3, 4. And once again, I'm just picking this because it's easy to write and it kind of rolls off my tongue. What would I add to this to get 1, 2, 3, 4? What do you think? Well, obviously each element you would add a 0, and the only tricky thing to this is that it must be the same size as the matrix that you're adding to. So if I had a matrix 1, 3, 4, right, which is a 1 by 3 matrix, the additive identity would have to be 3 zeros, 1 column and 1 row and 3 columns, so that it's identically the same size. All right, let's take a pause here. Okay, the last property that we're going to look at is the additive inverse. And if you remember in the real numbers, we would take 3 and we'd have to know what to add to get the additive identity. And you knew what you had to add was the opposite sign of what you started with. So that's very similar. So if we're talking about the additive inverse of a matrix, do an example, 1, 2, 3, 4, whatever we add to this, we want to end up with the additive identity, which is that. So I think you can tell that to every entry in this matrix, you would have to add the additive inverse in order to get the additive identity 0, 0, 0, 0 as your answer. So once again, this will work for all sorts of matrices. We could have a 2, negative 3, 4, 1, 8, negative 10, a 2 by 3. Oops. And if you wanted to add something to that, the additive, to get the additive identity, which is this, what would you add? Well, obviously, the opposite sign of all the entries in the first matrix, positive 10. Okay.